Unit 3, periodic table, looking at Chapter 2. Chapter 2 has us looking and identifying some things that are a little bit bigger on the periodic table. As Chapter 1 had us looking at some of the numbers on the periodic table. Now we're going to look at some other things that we can see in groups on the periodic table. First off, a little history. A few elements have always been known. They were for many years, it was just copper, silver, gold, known for thousands of years because they were found in their natural stable states. There were only 13 elements in the early 1700s. After that, what started happening is that others started discovering new elements. It's not unheard of, and the technologically advances that happened after the year 1700 kind of help us understand why those some of these had started to find. Now, iron and some of those were definitely easily found. Some of the other ones that had been found, not too many gases were found, but some of the early gases that can start to be found are ones that we do. As there became more elements, we had to figure out ways to organize them, because just listing them doesn't always work, because there's usually got to be a nice way to organize things as we look at it. In a decade of 5 elements being discovered is kind of a big deal. So when we start putting these together, we need to start figuring out a way to how to organize them. One of the first ways to organize them was done by Dmitri, and he put together what are known as triads. Triads, tri meaning 3, meaning we have groups of 3 elements. Some of them still exist on our periodic table. One of them, the most common one and easily seen, is the lithium triad, where you have lithium, sodium, and potassium compounds present, easily identified on our periodic table, as that would be the first one. And they all had similar chemical and physical properties, meaning how they looked and how they chemically reacted. A little bit later, Newlands suggested that the elements were more of a periodic fashion, meaning that they repeat. There is a repetitiveness to how these how these elements changed or reacted in their properties, and there was a periodicity to it. And he proposed the law of octaves. Now, I'm not sure if he was a music guy or not, and that's why we get the octaves, but octave means 8, and so every 8th one had a repetitiveness. And so it's such as like lithium, 8 elements later, you would have sodium, which if you really look at your periodic table, that still somewhat holds true, except for there are some interesting things that happen a little bit later on as more and more elements become discovered. We find that this isn't right, but the idea of a repetitiveness does happen. And if you look at where we are at in 1965, there are some things that are known about in this year, and that we do have some of the subatomic particles known about, but not all of the subatomic particles are known about at this time. A little bit later, Dmitri, Mendeleev, and Lothar Meyer independently arranged. Independently meaning they're doing the same work, completely different. Mendeleev being a Russian scientist, and Lothar Meyer, well, I'm going to guess that he was a German based on the strong German name of Lothar and Meyer. And so what they did was they were able to put together this idea of putting this periodic table together. They weren't able to Snapchat each other or Facebook saying, "Hey, guess what I did?" And instead, what you start to see is that these guys were doing the same work, independent of each other, published it probably within years of each other. But what Mendeleev did that was different than Meyer, and why we call Mendeleev the father of the periodic table, is not just how we ordered the elements, But something else that led us to kind of work within, and it's the important part of that he had some predictability to his periodic table. It wasn't just like here it is, and then 5 years later when we have to add more elements, we have to make a whole new one. That's might have been what Lothar Meyer had, where Mendeleev saw some gaps in the periodic table and said, there's these gaps, this is where these new elements are going to be, and he made some predictions about not just how they looked, or such as their physical properties, but also their atomic mass, which was kind of a stretch, and also their chemical properties as well. It's these prediction part, again, that we look at that really probably changed the difference between what Meyer did and what Mendeleev did. Mendeleev used that predictiveness to look at actually two elements on our periodic table that we are still currently have. And in the next slide, we'll actually see what Mendeleev's periodic table is, and we'll discuss that a little bit more when we look at that. But it's again that predictive component that Mendeleev had that Lothar Meyer did not. And when we look at this here, we can see that there are a couple gaps, and it's a few things look a little bit different, and one it's kind of on its side as opposed to kind of being up and down. There's a few of them that we can see that are still there and still hold true. We see that lithium, sodium, potassium, rubidium, cesium, they're all still together. We see that calcium, strontium, and barium are together, but lead being here doesn't make a lot of sense. Copper, silver, and mercury kind of somewhat a little bit. There's that. It kind of works. Beryllium and magnesium, they're together, but how does zinc fit in and cadmium fit in? And so there's some interesting things where some work, some don't. One of the other ones that we can see is fluorine, chlorine, bromine, and iodine, oxygen. There's so few of them. But now which ones that we want to really take a look at are the ones here in the red box where we have question marks. We don't know what those elements were at the time, and that's what Mendeleev predicted. He said that there should be an element that is similar to boron and aluminum and have an atomic mass of about 68. Well, if we look on our periodic table, there's not one that's exactly 68. Instead, we find one that is 69.723, which is gallium. Now again, Mendeleev based his periodic table on the atomic mass because the number of protons wasn't quite known about at this time. And so they were basing it off the atomic mass. And so then the next one we look at carbon, silicon, and an element somewhat similar to those two. Well, we find out that that's germanium. Even though the atomic mass on our periodic tables is 72.6, don't exactly know, but it should have some properties and somewhere around that. That ability to predict was extremely important. Now there are some other oddities as we see nickel and cobalt both having an atomic mass of 59. If we look on our periodic table, they're very close in their atomic masses, cobalt and nickel, and so their abilities to make those highly precise measurements wasn't there. Their abilities to do that just they couldn't do it. They didn't have a good scales, or the technology just wasn't there as the ones that we maybe have now. So using this, so some things needed to be switched, such as the ones that we talked about as cobalt and nickel, having ones that are very close. You have some inaccuracies, so in their calculations, and a lot of people were pretty happy with that. Some had to be switched so that you had some things working around for it. But for the most part, I think that if Mendeleev looked at our periodic table, that he would be able to recognize and go, oh yes, it's very similar to the way it is set up, the way we actually have it set up now. The periodic table that he did, again, was based on atomic mass, and ours, though not based on atomic mass anymore, looks very similar to that, because there are every now and then, there's about 5 odd ones out there, ones that are non-radioactive. Those would be the ones that are in parentheses on our periodic tables. Mendeleev arranged the elements in his periodic table in according to increasing a little bit later, a couple years, maybe even after Rutherford did his gold foil experiment, Moseley concluded that periodicity was more correctly based on the atomic number, or, as we saw earlier, the number of protons, rather than the atomic mass. And this gave us the periodic law. Their properties are reoccur in a repeating pattern, rearranged according to atomic number. So again, that's the number of protons. So, as we can see from this periodic table here, this is what the periodic table would look like if we didn't have the lanthanoid and actinoid series just separated off. Looking down, there would be a few that are missing as well on here, but again, we're not really worried about those ones because we don't come in contact with those all that much. So, for the most part, this is what it is, and has gone, for the most part, unchanged, except for the addition of elements over the last 103 years plus. The modern periodic table has elements arranged in order of Now, looking at the organization of the periodic table, and first off, a period was a horizontal row, and a horizontal row, again, is something that moves in the horizontal, such as in the horizon. That would be the left to right. And we look at a period moves from left to right, and they are numbered, starting at the top, with numbers as 1, 2, 3, all the way down to 7. As we saw last time, we called those the principal quantum number, and so these periods. And at the end, and one way to remember this is if you were writing a sentence normally, you would write it from left to right, and at the end of most sentences goes a period, and so the periods move from left to right on the periodic table. Groups or families or columns in the periodic table. Groups are numbered starting at the left and moving to the right. Most of the elements within a group or family have very similar properties. Just like in our own families, as spread out and nuclear as they might be, people have similar properties. I know a lot of people probably have heard it time and time again. Oh, you look just like so-and-so. And as much as you might not enjoy being said, oh, you look like so-and-so, you are going to have some similar properties because you're a part of a family, and therefore you will have some similar traits. It's part of the genetics that you have. You will have some of those traits on how you look. Well, that's kind of the physical properties that these elements have. How you physically look and how the elements physically look are going to be somewhat the same. You might not be exactly the same as so-and-so. It's just like lithium. It does not look exactly like sodium does. They have some similar properties, but they're different, and that's what makes the periodic table, and sometimes where we can use these humanistic qualities to kind of show that there's some similarities, and we can kind of see a little bit of relationship to how we live our lives and how the periodic table is also organized, such as groups or families. We're organized based on how we look for the most part, and those are similar traits, physical properties for elements. You're going to find these numbers. There's 2 sets on most periodic tables. I wrote in the American notation on our periodic table. That's why I didn't use Roman numerals. And that's indicated with the orange arrow, which is the 2 A's and the 3 A's. And if you look on the transition metals, you have the 3B, 2B, 4B, and so on and so forth. The American notation can be somewhat confusing because you have this weird thing that happens between groups 8, 9, and 10 in the transition metals, and that's one big group. And what happens is that group does have some very similar properties. All three of those groups have some very similar properties, and that's why the American way of doing it puts together. For the most part, though, I prefer the IUPAC notation, and that's numbering them 1 through 18, because you only have to worry about numbering them as you see them on the periodic table. I feel so much easier to understand than the American notation. Now, when we look at the periodic table, there's some other trends that we see. As we can see, it's colored a little bit differently. My suggestion is getting a fresh new periodic table and coloring your periodic table that you use for tests and such as that the same way, where metals are colored in one way and non-metals are colored in a different way, and metalloids are colored in a different way. That is my strong suggestion. Why? That's because when we get into some of the naming and some of the bonding, it will be very useful for you so that you can see what kind of naming you have, because is it a metal or is it a non-metal? Especially what the compound starts with. And so when we get to doing that, you'll have that there. And so my suggestion is to do that part of it, is to color your periodic table with 3 different colors. I have crayons and colored pencils in my room. So if you're in my room, I would suggest just getting up and getting a fresh new periodic table and coloring them. If you choose to use highlighters, feel free to use highlighters. I would use colors that you will be able to see the little charges that are in the other right-hand corner, and the numbers as well, as those will become very useful as we move forward. More specifically, looking at these groups, the metals occupy the left 3/4 of the periodic table. They are the majority of our periodic table. Metals, for the most part, does not mean all of them are good conductors of heat and electricity. Some conduct heat and electricity better than others. Copper, probably pretty good, considering that we use it for a lot of our electrical circuits, although gold is better. Why don't we put gold in our houses? Well, it becomes a cost factor. But silver is actually the best, but because, again, of cost and actually how it oxidizes, meaning it reacts with oxygen, makes it not as good of a one to use. They tend to be a bright metallic luster. That's what makes them highly sought after. That's the bling bling part of it as well, with that bright metallic luster. They're malleable. That means they're able to be hammered into sheets for artwork or other means. Ductile, meaning they're able to be drawn into wire, meaning it's pulled into wire. Kind of as you would draw the bow back on a bow and arrow. It would be drawn back, and it's pulled into sheet wire, as we see. So for other wires, as we have a lot of different types of wire, not just copper wire. It should come at no surprise that the metals, for the most part, are solids at room temperature, with the exception of mercury, which is the only liquid. It's not really liquid mercury that becomes a major problem, as why people are always so afraid of mercury, but instead it's actually mercury vapor, because if you spill mercury on the carpet, usually a lot of people don't think about it, and then actually what happens is that you have mercury vapors when depending on how the vacuum works, and that can be very dangerous as well. It also leads us to looking at the Mad Hatter idea, is what mercury came from, is because they use hatters when they were actually, people wore hats, like a bowler hat. They used hats to help form the brim and the hat itself and keep it hard. And what that was, the hatter, the person who made the hats, would dip their hands in the mercury and use it to form the brim and the hat itself. And so actually, from Alice in Wonderland, the Mad Hatter is not a reference to some drug or anything, but instead is talking about mercury poisoning, which is a neurological disease. Metals tend to have low ionization energies, thus forming cations, meaning they form a positive charge. As you look on your periodic table, the metals will all have a positive charge on the upper right hand corner of those, and that happens fairly easily and readily. We'll look at ionization energy and trends in chapter 3, but it's not a bad idea to talk about that, at least hear the term before. Some of the more important compounds, such as metal oxides, copper has a very important metal oxide, is that that copper oxide forms, that green copper oxide forms, and actually forms a protective cover for the rest of the copper. And that's why sometimes they use it in artwork. One, because they know it actually will turn green with the anticipation of that. That's why the Statue of Liberty is green. They knew it was actually going to turn green. Some people even will put it on their roofs of their buildings. Some of these metal oxides tend to be very basic, meaning they are not an acid. Basic, not simple, but instead basic, meaning not an acid, which are not a general property of metals. Non-metals, well, they're not metals. And occupying the right quarter of the periodic table, they're a very small group on the periodic table. Metals are not good conductors of heat and electricity. That doesn't mean that they can't, it's just that they're not very good at it. They typically have dull in color. Most of them are very rarely solids to begin with. They're not malleable. You can't pound them into sheets. They're not ductile. They won't be drawn into wire. They can be pressed into pellets, but that's not really all that useful if you're going to try to build a statue or something similar to that. Now, these nonmetals, a lot of them are very important when it comes to our everyday life, and that is the 7 diatomic molecules. This is going to be the first time, but we'll talk about these time and time again. And the 7 nonmetals that exist as diatomics, meaning they exist as a molecule, such as hydrogen, and let's look at nitrogen, oxygen, that's O2, that's actually what we breathe, fluorine, chlorine, bromine, and iodine all exist as a molecule in that. All of them are gases except for bromine and iodine, where bromine is a liquid, iodine is a solid. The ways to memorize the diatomic molecules can be looked at as H NOF, H for hydrogen, NOF, and then chlorine, bromine, and iodine is down. So I usually say what the H NOF and down. Or another way to look at it is draw a 7 starting at 7, and if you start at element 7, nitrogen, and draw a 7, you would actually have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Then you just have to remember the 7th one, hydrogen. The noble gases, well, they're gases, and were actually very difficult to discover because they don't react with anything, hence the idea of nobility. They do not interact with common elements, and so they do not interact or react with other elements. They do, however, react in some cases, just extremely rare and under extreme circumstances or conditions. They, for the most part, are solids, and that would be like carbon is a solid, silicon is a metalloid, but phosphorus, sulfur, or a few other ones. They like to gain electrons, that meaning they'll form anions, and then they will have nonmetals will also form with other nonmetals. That's why we wanted you to color your periodic table so that you can identify your nonmetals easier. And then you will see that they exist as acidic acids on the back of your periodic table. A lot of them will be on there as the nonmetal with oxygen being one of the other nonmetals, and the polyatomic ions. And those are very special group of ion molecules. And the last group of elements on the periodic table is the ones that are kind of touching that darkened stair-like line on our periodic table, and they separate the metals from the non-metals, and these are the metalloids or semi-metals. Kind of have an identity crisis in that they're not metals and they're not non-metals. They kind of have properties of both. Some of them would look very metallic if you saw them, such as silicon and antimony. Look very metallic when you see them in their natural stable state, but chances of you seeing them in their natural stable state is actually quite odd in that to look at it, silicon looks very kind of black, dark, and glassy. And antimony looks dark, and it will also look kind of have a metallic shimmer to it as well. And these are very important in how we use them. Now, it's not to say that nothing has ever changed over the years. Every now and then, I've seen periodic tables now that have acetine number 85 in the little corner there as actually a metal, and I've seen it as a non-metal. And so sometimes we have a tough time trying to figure it out. When I was in high school many years ago, aluminum was a metalloid, and now its metallic properties have kind of shined through. Pun intended. And so these metalloids, because a common general rule is if it touches that black stair line, it's a metalloid. And for the most part, you're going to be right. There's just a couple of them that you would miss out on. And, a lot of times that can be fine. It's just these general trends and kind of just looking at the periodic table and figuring out, is it a metal or a non-metal? Chances are, if you can find the metalloids or that darkened kind of line and kind of say to the left it's your metals, to the right it's your non-metals, and if it touches it, it's your metalloids, you're going to be doing yourself just fine.